Infinity has a powerful allure. It feels like the correct answer. When somebody poses the question of the universe's true size, replying that it is infinite feels satisfying, almost profound. It aligns perfectly with our deep-seated intuition that the cosmos should be ultimate, limitless, without any border or confinement. The notion that space simply continues forever in every direction, with no end in sight, feels inherently right in a way that a universe with limits never could. And it's the default assumption held by nearly everyone. Cosmologists, research physicists, science communicators, and the broader public, when they picture the universe, they envision something boundless. Space extending outward endlessly in all directions. Today, I want to challenge that deeply ingrained assumption, not because I possess absolute proof that the universe is finite, I don't, but because the question itself is far more nuanced and complex than most people realize. And because the evidence, when scrutinized carefully, does not overwhelmingly point toward infinity. In fact, it might suggest the exact opposite. The universe could very well be finite. I'm not referring to the observable universe, which is obviously finite, bounded by the maximum distance light has been able to travel since the Big Bang. I mean the total universe, the entirety of space, everything that exists. And if it is finite, it could be finite in ways that are profoundly strange, ways that involve no edge, no boundary, no cosmic wall. A finite universe you could theoretically traverse without ever encountering an end, yet one that contains a finite total amount of space. This is not some fringe idea on the outskirts of science. It is serious cosmology, constrained by actual observational data and motivated by genuine theoretical considerations. Let me walk you through why the universe may not be infinite and what that would actually mean for reality. First, we must establish a critical distinction. The observable universe is not the universe. Let's be crystal clear about something that is almost always blurred in casual discussions. The observable universe refers specifically to the region of space from which light has had sufficient time to reach us since the dawn of the cosmos. The universe is approximately 13.8 billion years old. Light travels at a finite speed of roughly 300,000 kilometers per second. So, a naive calculation might lead you to think the observable universe extends about 13.8 billion light-years in every direction. However, the universe has been continuously expanding ever since the Big Bang. The regions that emitted the earliest light we can detect, the cosmic microwave background, were actually much closer to us at the moment they emitted that light. They have since been carried much farther away as space itself stretched. The net result is that the observable universe now extends roughly 46 billion light-years in every direction. We exist within a sphere with a radius of about 46 billion light-years, not 13.8 billion. That 46 billion light-year figure accounts for cosmic expansion. Everything contained within this sphere is, in principle, accessible to our telescopes and observations. Everything lying beyond it is not. Light from those distant regions simply hasn't had enough time to reach us. That territory is causally disconnected from our own. But the universe almost certainly extends far beyond this observable bubble. The real question is, by how much? There are three fundamental possibilities. First, the universe is truly infinite. Space stretches on forever, in every direction, without any limit whatsoever. This would mean an infinite volume containing an infinite number of galaxies, stars, planets, and presumably an infinite number of copies of everything, including you. Second, the universe is finite but unbounded. It possesses a finite total volume, yet has no edge, no wall, no boundary. Think of the surface of a sphere, but extended into 3 dimensions. Third, the universe is finite and has an edge. Space simply stops somewhere. Beyond that edge is nothing. Not empty space, but literally nothing at all. That third option is philosophically incoherent and observationally disfavored. Every measurement of spatial curvature we have made suggests that space is, at least locally, flat. If space had a physical edge, you would expect dramatic curvature to appear near that boundary. So the real debate, the meaningful scientific question, lies between the first two possibilities. infinite versus finite, but unbounded. And the answer hinges entirely on the global topology of space, something we are only just beginning to probe observationally. To understand this properly, we need to grasp the difference between geometry and topology. Most people never encounter this distinction, but it is absolutely vital. Geometry deals with local measurements, distances, angles, curvature. It tells you whether space is flat, positively curved like a sphere, or negatively curved like a saddle. You can determine geometry by making measurements in your immediate vicinity, such as measuring the angles of a triangle or observing how parallel lines behave. Topology, on the other hand, concerns global structure, connectedness, how the entire space fits together as a whole. You cannot determine topology from local measurements alone. Consider the surface of a donut and the surface of a sphere. Locally, they can have identical geometry. Both can be flat if you zoom in enough, but their global topologies are completely different. The curvature of space and the topology of space are independent properties. Flat space can accommodate many different topologies. Positively curved space can also have various topologies. Einstein's field equations determine the geometry of space-time based on the distribution of matter and energy, but they say nothing directly about global topology. Topology is an additional piece of information, not determined by Einstein's equations. This is a crucial point. When cosmologists measure the curvature of the universe and find it to be flat or nearly flat, they are measuring the local geometry. They are not measuring the global topology. A flat universe can indeed be infinite. That is the naive expectation. But a flat universe can also be finite. There exist flat tori, flat cylinders, flat Klein bottles. There are flat geometries with finite volumes and various topological structures. The simplest example of a finite flat universe is the three torus. Imagine taking a cube of space and identifying opposite faces. If you travel far enough in the x direction, you simply reappear from the opposite side, just like in the classic video game Pac-Man. The same holds for the y direction and the z direction. The resulting space is finite, completely flat, and has no boundary. You would never reach an edge, but if you continued traveling in any straight line, you would eventually return to your starting point. This is not the only possibility. There are 18 distinct topologies for flat three-dimensional spaces. For positively curved spaces, there are more. For negatively curved spaces, there are infinitely many possible topologies. The universe could possess any of these topological structures, and we would need very careful observations to determine which one is actual. So, what do our actual measurements tell us about the universe's size and topology? Our most powerful tool for this investigation is the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang. It is light that was emitted approximately 380,000 years after the beginning, now cooled to a mere 2.7 degrees above absolute zero, and spread uniformly across the entire sky. Crucially, the CMB contains fluctuations. These are tiny temperature variations, on the order of 1 part in 100,000, that encode profound information about the structure of the early universe. These fluctuations possess a characteristic power spectrum, a distribution showing how much variation exists on different angular scales. If the universe has a finite size, if it is wrapped around on itself in some way, then there exists a characteristic scale, the size of the universe itself. Fluctuations on scales larger than this fundamental size simply cannot exist. They would be cut off. The power spectrum would then exhibit a suppression at very large angular scales, at low multipole numbers in the spherical harmonic decomposition. And here is where things get interesting. The CMB power spectrum does, in fact, show an anomalously low quadrupole. The largest scale fluctuations, corresponding to patterns that span the entire sky, are weaker than what the standard infinite universe model predicts. Could this be because the universe is finite, with a size comparable to the Hubble length, about 46 billion light-years? It is a real possibility. Alternatively, it could be due to cosmic variance, which is the statistical noise inherent in having only one sky to measure. With a single universe, we can only make one measurement of each multipole, and random statistical fluctuations can suppress any given mode purely by chance. The observed suppression is not statistically overwhelming. It is intriguing, certainly, but far from conclusive. The simplest interpretation of current CMB data is consistent with an infinite universe, but it is equally consistent with a universe that is finite, with a size on the order of the Hubble volume or perhaps somewhat larger. What concrete constraints can we place on the size? If the universe were smaller than a certain threshold, we would expect to see matched circles in the CMB. In a finite universe with an appropriate topology, the last scattering surface, the spherical shell from which the CMB photons were emitted, would intersect itself. This self-intersection would create identical circles of temperature fluctuations appearing on opposite parts of the sky. Extensive searches for such matched circles have been conducted. So far, no convincing matches have been found. This tells us that the universe, if it is finite, must be larger than a certain minimum size, roughly the diameter of the observable universe, which is about 90 billion light-years. A universe smaller than this would have produced detectable matched circles. But 90 billion light-years is not infinite. The universe could be finite at 100 billion light-years, 1 trillion light-years, or even 1 Google light-years. All of these are finite and entirely consistent with current observations. The universe simply has to be large enough that any signature of its topology falls beyond our observational horizon. With our current technology, we cannot definitively determine whether the universe is infinite or finite. We can, however, state that a finite universe with a size much larger than the observable region is observationally indistinguishable from an infinite one. Another direct observational approach involves measuring the universe's curvature. In general relativity, the geometry of the universe is linked to its energy content. Specifically, the curvature is determined by whether the total energy density of the universe equals, exceeds, or falls below a critical value. If the actual density equals the critical density, the universe is spatially flat, adhering to Euclidean geometry, much like an infinite flat plane. If the density exceeds the critical density, the universe is positively curved, analogous to the surface of a sphere, but in 3 dimensions. Positively curved universes are necessarily compact and finite, with no boundary. If the density is below the critical density, the universe is negatively curved, like a saddle surface. Negatively curved universes can be either infinite or finite, depending on their topology. Cosmologists use a parameter called omega, which is the ratio of the actual density to the critical density. If omega is exactly 1, the universe is flat. If omega is greater than 1, it has positive curvature. If omega is less than 1, it has negative curvature. Current measurements from the Planck satellite and other CMB data give a value for omega that is very close to 1. The best measurement is omega equals 1, plus or minus 0.02. This is perfectly consistent with a flat universe. If omega were exactly 1, the simplest interpretation would indeed be an infinite flat universe. However, given the measurement uncertainty, omega could actually be 1.001 or 0.999. These tiny departures from perfect flatness have dramatic implications for the universe's total size and curvature. If omega equals 1.001, just slightly above 1, then the universe is positively curved. A positively curved universe is closed and finite, taking the shape of a 3-sphere. Its total circumference would be enormous, far beyond the observable universe, but it would be undeniably finite. Just how enormous? For a universe with omega equal to 1.01, the circumference of this closed universe would be approximately 5 times 10 to the 23rd power light-years. That is staggeringly larger than the 90 billion light-year observable universe, but it is finite. So even if omega is only barely above 1, well within our current measurement uncertainties, the universe could be finite, just vastly larger than the region we can observe. Conversely, if omega is exactly 1 or just below 1, the universe could still be finite if it possesses a non-trivial topology. Curvature constrains geometry, but it does not constrain topology. A flat universe with a 3-torus topology is finite. A negatively curved universe with a specific topology can also be finite. The measurement of omega being close to 1 neither confirms nor rules out a finite universe. It merely narrows the range of possible scenarios. The theory of inflation, which posits a period of rapid exponential expansion in the very early universe, has profound implications for the universe's size. Inflation elegantly solves several major cosmological puzzles: the flatness problem, the horizon problem, and the monopole problem. It explains why the universe appears so remarkably uniform on the largest scales and why its geometry is so close to flat. But inflation also has an implication for the universe's size that is frequently overlooked. Before inflation, the region that would eventually become the entire 46 billion light-year sphere we now observe was an incredibly tiny patch, smaller than a subatomic particle. Inflation then expanded this minuscule region by a factor of at least 10 to the 26th power in a fraction of a second, and possibly by much, much more. The exact duration and magnitude of inflation are uncertain. The total universe, whatever its extent might have been before inflation began, was also inflated by this same enormous factor. If the pre-inflationary universe was only just barely larger than the region that would become our observable universe, then after inflation the total universe would be only just barely larger than our observable universe. It could potentially be only a few times larger, possibly finite, with a size not much greater than what we can currently see. But if inflation lasted longer, if the expansion factor was, say, 10 to the 100th power, then the total universe would be 10 to the 100th times larger than the observable region. For all practical purposes, that is effectively infinite. Yet, technically, it would still be finite if the pre-inflationary universe itself was finite. Inflation does not tell us that the universe must be infinite. It tells us that the total universe is at least as large as what inflation made it. The minimum possible size depends on how long inflation lasted. The maximum possible size is entirely unconstrained. It could have been finite or infinite even before inflation began. Here is an interesting argument to consider. If the pre-inflationary universe had some finite size, if it originated as a quantum fluctuation, for instance, with a finite initial volume, then even after the immense expansion of inflation, the total universe would remain finite. It would be enormously larger than the observable region, but finite nonetheless. Quantum cosmological models, such as the Hartley-Hawking no-boundary proposal, suggest that the universe came into being as a quantum fluctuation with a finite initial volume. It then underwent inflation. In this picture, the total universe is finite, though potentially vastly larger than the part we can observe. Inflation, when combined with certain quantum cosmological models, actually motivates a finite universe rather than an infinite one. The universe began with a finite volume and was inflated to a larger but still finite volume. Let me now explain why many physicists are deeply uncomfortable with a truly infinite universe. This discomfort is not merely philosophical, it is physical. Infinity creates serious technical problems within our theoretical frameworks. Problem number 1. Infinite volume implies infinite matter. An infinite flat universe with a uniform distribution of matter contains an infinite total mass energy. It contains infinite numbers of galaxies, stars, particles, infinite entropy, infinite everything. Some cosmologists are perfectly comfortable with this. Others find it deeply problematic. An infinite universe would mean that every possible event, including every possible configuration of matter, occurs not just somewhere, but an infinite number of times. There would be infinitely many copies of you, of Earth, of the Milky Way. Not just a few copies scattered throughout space, but an infinite number. This leads to severe, perhaps insurmountable problems with probability and statistics. If every conceivable outcome occurs an infinite number of times, how can you possibly assign meaningful probabilities to events? The ratio of favorable outcomes to total outcomes becomes infinity divided by infinity, which is mathematically undefined. Statistical reasoning, the very foundation of scientific inference, collapses. This is intimately related to what cosmologists call the measure problem. It is the problem of defining sensible probabilities in an infinite universe, and it is a genuine, unresolved technical challenge. Problem number 2, Boltzmann brains. In an infinite universe, rare quantum fluctuations are not just possible, they are inevitable. Given infinite time and infinite spatial volume, fluctuations of arbitrarily high complexity will occur purely by chance, somewhere, at some time. A Boltzmann brain is a hypothetical conscious observer that forms spontaneously from such a random fluctuation, complete with false memories of a history that never actually happened. In an infinite universe, such entities would occur infinitely often. This is not just a philosophical curiosity, it is a statistical catastrophe. In an infinite universe, randomly fluctuated observers like Boltzmann brains should vastly outnumber evolved observers like us, who have arisen through the long, orderly process of cosmic and biological evolution. If we are typical observers, we should expect to find ourselves to be Boltzmann brains with fabricated memories, but we do not. We appear to be consistent, long-lived observers situated within a large, orderly universe. This is the Boltzmann brain problem. A finite universe, by contrast, limits the total number of possible fluctuations. It does not entirely eliminate the Boltzmann brain problem, but it renders it far less acute. You cannot have an infinite number of fluctuations if you have a finite volume and a finite amount of time. Problem number 3, initial conditions. If the universe is infinite, specifying its initial state would require an infinite amount of information. The initial quantum state of an infinite universe would be infinitely complex. This is technically problematic and philosophically uncomfortable. A finite universe, on the other hand, possesses a finite initial state, a finite amount of information, a wave function that can, in principle, be written down and analyzed. This is far more tractable, both technically and conceptually. None of these problems constitute proof that the universe is finite. However, they strongly suggest that an infinite universe carries significant theoretical costs that a finite universe neatly avoids. Now, the discussion becomes even more interesting and complex when we consider the multiverse. In the picture of eternal inflation, which I have explored in other contexts, our observable universe is just one bubble within an eternally inflating space-time. Other bubbles exist, each potentially possessing different physical constants, different particle physics, and different cosmological properties. The total structure, the multiverse, is vast and possibly infinite. But, and this is the crucial point, each individual bubble, each pocket universe, might itself be finite. A single bubble could have a finite total volume. The multiverse as a whole is the infinite structure, while the individual universes contained within it are finite. This is actually the more natural picture that emerges from eternal inflation. When inflation ends in a particular region, when a bubble nucleates and a pocket universe forms, the resulting spacetime typically has the geometry of an open universe, either negatively curved or flat, and it could be finite, depending on its topology. In string theory, the landscape of possible vacuum states provides a vast array of possible universes with different physical properties. The estimated number of distinct vacua is on the order of 10 to the 500th power. Each of these might correspond to a different pocket universe. Each pocket universe might be finite. The multiverse picture thus offers you infinity at the meta level within the eternally inflating space-time, while simultaneously allowing individual universes like our own to be finite. This might be the ultimate resolution. Our universe is finite, but embedded within an infinite structure containing other finite universes. This picture has a pleasant feature. It preserves the sense of infinity that many cosmologists feel is physically necessary, while also providing the technical and philosophical advantages of finite individual universes. However, I must be honest, this is highly speculative. We have no direct evidence for the multiverse. We have strong theoretical motivations within certain frameworks, but no observation has yet confirmed the existence of other bubble universes. Let's try to imagine what it would actually be like to live in a finite universe. What would you observe? What would be different? If the universe is a 3 torus, the simplest finite flat topology, then in principle, You could travel in any straight line direction and eventually return to your exact starting point. It would be like circumnavigating the globe, but in 3 dimensions. You would never encounter a wall. You would never reach an edge. You would simply keep going, and after traveling a distance equal to the size of the torus, you would find yourself back where you began. You would also potentially observe something else, the same cosmic objects appearing in multiple directions. In a sufficiently small, finite universe, light could have enough time to travel all the way around and come back to you. You might look out in one direction and see the Milky Way, our actual galaxy. Then you might look in an entirely different direction and see the same galaxy from a different angle, its light having completed a full circuit of the universe to reach you. This is known as cosmic crystallography, the search for the same objects appearing multiple times in different parts of the sky. We have looked for such patterns. We have not found compelling evidence for them. This tells us that the universe, if it is finite, must be large enough that we cannot see these multiple images within our observable volume. If the universe is a 3-sphere, a positively curved closed space, you would live in a space that is topologically a hypersphere. There is no preferred center. Every point is equivalent. Traveling in any direction, you would eventually return to your starting point. The total distance around such a universe would be the circumference of the 3-sphere. In this scenario, you could look in the exact opposite direction in the sky and potentially see the back of your own galaxy, or more accurately, an image of our galaxy as it appeared long ago, its light having traversed the entire universe. We have not detected this either, which places another constraint on the minimum size of any closed universe. The key observational signature, as I mentioned earlier, is the matched circles in the CMB. In any finite topology, if the universe is small enough, the last scattering surface will intersect itself, creating those identical circles. We have searched carefully and found nothing. The universe is therefore either truly infinite or finite, with a size so large that the matched circles fall outside our observable volume. Either way, the signature of the universe's topology remains hidden from us by the fundamental limitation of how far we can see. Here's another argument suggesting that the universe might be finite, or at least that the concept of infinite space might be physically meaningless. In quantum gravity, particularly in approaches like loop quantum gravity, space is not a continuous fabric. It is discrete. Area and volume come in minimum, indivisible units at the Planck scale. There exists a smallest meaningful length, the Planck length, which is about 10 to the minus 35 meters. In a discrete space-time, the concept of an infinite volume takes on a different meaning than in a continuous space-time. Infinite volume would mean an infinite number of Planck-scale cells. This is mathematically conceivable but physically questionable. More fundamentally, if space-time itself is quantized, and if the universe had a quantum origin, a finite quantum state from which everything emerged, then the total number of degrees of freedom might be finite. The total information content of the universe might be finite. The holographic principle, which has been a central focus of much of my career, gives a specific form to this idea. It states that the information content of any region of space is bounded by the area of its boundary, measured in Planck units. This sets a finite maximum information density. For a finite region, this implies a finite total information content. For an infinite universe, it would imply an infinite information content. But if information is fundamentally finite, if the quantum state of the universe possesses a finite Hilbert space dimension, then the universe itself must be finite. This is speculative. I want to be very careful here. These are arguments, not proofs. The holographic principle does not directly imply that the universe has a finite volume. However, it does suggest that infinite space, if it exists, might be physically redundant. It raises the possibility that all the physics could ultimately be captured by a finite dimensional description. The idea that the universe might be finite in some fundamental informational sense, even if not obviously finite geometrically, is one that I take seriously. It emerges naturally from careful thinking about quantum gravity and holography. Let me be direct about something that scientists rarely state so openly in public discussions. Infinity is hard to deal with. Not just philosophically hard, but physically hard. Infinities in physics almost always signal a breakdown of the current theory. When quantum field theory calculations produce infinite answers, we employ renormalization. We absorb those infinities and extract finite physical predictions. When general relativity predicts an infinite density at the moment of the Big Bang or inside black holes, we interpret this as a clear signal that general relativity is incomplete, that a theory of quantum gravity must take over before the actual infinity is reached. Every single time physics has encountered an infinity, it has treated it as a problem to be solved, a sign of theoretical incompleteness. So why should the universe itself be infinite, when every infinity that appears in our equations is consistently interpreted as an indication that something is wrong with our understanding? A truly infinite universe would possess infinite total energy, infinite total entropy, infinite total mass. These are not quantities that appear naturally in any finite physical theory. They suggest that our ordinary physical concepts break down entirely. Perhaps the correct interpretation is that the universe is not in fact infinite. Our current theories, which predict or allow for an infinite size, are incomplete. The correct theory, quantum gravity or whatever comes next, will describe a universe of finite total size, just as it will presumably replace the infinite density, singularities at the Big Bang, and inside black holes with something finite and well-behaved. This is not a rigorous proof, but it is a reasonable heuristic drawn from the entire history of physics. Infinities are problems. If the universe appears infinite to our current theories, perhaps that is a problem to be solved, not a fundamental truth to be uncritically accepted. I also want to be honest about the psychological dimension of this question. The appeal of an infinite universe is, to a significant extent, psychological rather than physical. An infinite universe feels grander, more ultimate, more in line with human intuitions about what the cosmos should be. We feel that the universe should not be merely a finite volume, like a very large room. It should be infinite, unbounded, without any limit. This feeling is completely understandable, but it is not a physical argument. Our intuitions about what the universe should be like were shaped by evolution on a small planet over a tiny timescale. Our intuitions are adapted to the African savanna, not to cosmological scales. There is absolutely no reason to trust them as reliable guides to the ultimate structure of reality. The entire history of science is a history of counterintuitive truths being forced upon us by evidence. The Earth is not the center of the solar system. The Sun is not the center of the galaxy. The universe is not static. Space itself is curved. Time is relative. Nothing is truly solid. If the universe turns out to be finite, if the total volume of all of space is some enormous but definite number, this would be yet another counterintuitive truth. It would go against our deepest instinct that space should just go on forever. I do not know if the universe is finite. Nobody does. Current observations are perfectly consistent with both possibilities. But I want to push back strongly against the assumption that infinity is the obvious or natural answer. It might be the correct answer, or it might be wrong. Just like every other naive assumption about the cosmos that humanity has ever held has ultimately been proven wrong. Let me conclude by summarizing the honest state of our knowledge. We do not know whether the universe is finite or infinite. Current observations are incapable of distinguishing between a truly infinite universe and a finite universe that is simply much larger than the observable region. Here is what we do know. The observable universe is finite, with a radius of about 46 billion light-years. The total universe certainly extends beyond this. How far? We do not know. Here is what the geometry tells us. The universe appears spatially flat, consistent with omega equal to 1. This is consistent with an infinite flat space, but it is also entirely consistent with finite topologies, such as flat tori or slightly curved closed spaces that would be indistinguishable from infinite flat space with our current technology. Here is what topology searches tell us. Searches for matched circles in the CMB have found nothing, placing a firm lower bound on the universe's size. If it is finite, the universe is at least as large as the observable region, and possibly much, much larger. Here is what theoretical physics suggests. Considerations from quantum gravity, holography, and the historical treatment of infinities in physics all provide indirect motivation for thinking the universe might be finite. These are not proofs, but they are arguments that deserve to be taken seriously. Here is what infinity costs. An infinite universe creates profound, perhaps insurmountable, problems with probability, Boltzmann brains, and the very meaning of physical predictions. A finite universe neatly avoids these specific problems, though it undoubtedly introduces others. My own view is one of genuine uncertainty. I find the arguments for a finite universe to be far more interesting and potentially more compelling than they are usually given credit for in popular discussions. The widespread assumption of infinity is surprisingly weakly justified. The evidence suggestive of finitude is intriguing, though far from conclusive. What I am confident about is that this is a real, open scientific question, not a settled matter. The universe might be finite, and if it is, that realization would fundamentally transform our understanding of probability, cosmology, and the very nature of existence. The universe is under no obligation to be infinite just to satisfy our sense of cosmic grandeur. It only needs to be what it is. And what it is, we are still in the process of figuring out.